Alright, so last time we talked about arithmetic sequences and how to find the sum of an arithmetic sequence. Today we're going to continue our discussion on sequences and sums by talking about what we call geometric sequences. So what is a geometric sequence? A geometric sequence is a sequence where the ratios between consecutive terms is the same. So with arithmetic sequences, it was the difference between consecutive terms that was the same. But with geometric sequences, it's a ratio that's the same. So for example, for this sequence here, A1, A2, A3, A4, A5, in order to find what we call the common ratio, we would divide one term by the term before it. So A2 divided by A1 would be the same as if we were to do A3 divided by A2, A4 divided by A3, and so on. And so you can see what we're really doing here is we're really finding what R has to be. In other words, what number do I multiply to get to the next term? Okay. Now, one thing to note, R cannot equal 0 for this to work. And then we call R the common ratio of that geometric sequence. Okay, so take a look at example 1. Determine the common ratio in the following geometric sequences and find the following three terms. Okay, so for the first example, it might actually be pretty easy to figure out what we need to multiply by in order to get the next term. Really, probably what you're doing very quickly in your head is you're doing 4 divided by 2 is 2, 8 divided by 4 is 2, so you're just multiplying by 2 each time to get to the next term. So that means R, the common ratio, is equal to 2. And then to find the following three terms, we just have to continue multiplying by 2. So 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. So your next three terms are 16, 32, 64. Okay, for the second one, this might not be quite as easy. We have negative 1/3, positive 1/9, negative 1 over 27, and so on. So you have to ask yourself, what do I need to multiply by in order to get to the next term? Now the first thing to notice is that the first term is negative, the second is positive, the third one is negative. What does that mean? That must mean that R has to be negative. So if you do a negative times a negative, you get the positive number. Positive times a negative gives you the negative number. So clearly, R is negative. Now that we figured that out, now let's just focus on the values without the positives and negatives. So 1/3, then 1/9, then 1 over 27. So it looks like we're multiplying the denominator by 3, and in the numerator, we're just multiplying by 1. All right, so that must mean that the common ratio R is equal to negative 1/3. And you can verify this. Negative 1/3 times negative 1/3 is positive 1/9. 1/9 times negative 1/3 is negative 1 over 27. And then now we need to find the following three terms. So let's go ahead and multiply negative 1/27 by negative 1/3. That gives us 1 over 81. Multiply that by negative 1/3. That gives us negative 1 over 243. And multiply that by negative 1/3, and that gives us 1 over 729. Okay, so just like arithmetic sequences, we are going to start off by talking about how do you find the nth term of a geometric sequence so that you don't have to go about calculating every single term in the sequence until you get up to the 50th term, for example. So here's the formula for that. The nth term of a geometric sequence is going to be a sub 1, so the first term, times R, the common ratio, raised to the n minus 1. Now we saw this n minus 1 in arithmetic sequences as well, but instead of being in the exponent, the n minus 1 was multiplied by d because you were adding d n minus 1 times. In this case, with a geometric sequence, what we're really doing here is we are constantly multiplying by R. But how many times do we multiply by R? we multiply by r n minus 1 times. And so it's in the exponent because that's how many times you are multiplying by r. Okay? And you can write down a sub 1 is the first term of the sequence, and r is the common ratio. Okay, let's do an example where we use this. So this example says, find a formula for the nth term of the geometric sequence below, and use the formula to find the 10th term in the sequence. Okay, so we have 3, 6, 12, and it continues. Okay, so clearly the first term is 3. Now, we're told it's a geometric sequence, so that means we're multiplying by a certain number to get to the next. It looks like we're multiplying by 2, right? 3 times 2 is 6, 6 times 2 is 12, and so on. So r is equal to 2. And now we can go ahead and plug this in to get the formula. So a1 is 3, and r is 2. So this is the formula here. Be really careful to leave this formula in this way. Do not multiply the 3 and the 2 to try to simplify it. Why? Because you do the exponents first. If you don't know what n is and you haven't subbed in for that yet, you just leave it as is. When you use the formula, you'll plug in a value for n, raise 2 to that power before multiplying by 3. If you multiply the 2 and the 3 together, then you're raising 6 to the n minus 1 power, and that's not what you want to do. Okay, so the second part is to use the formula to find the 10th term in the sequence. So we're going to plug in 10 for n. So that's 3 times 2 to the 10 minus 1. So that's 3 times 2 to the 9th, which is 512. And now you multiply 3 times 512, and that is equal to 1,536. So the 10th term in the sequence is 1536. All right, the next example is slightly different. Let's take a look. It says the 4th term of a geometric sequence is 8, and the 10th term is 512. Write a formula for the nth term and use it to find the 15th term in the sequence. Okay, let's write down what we have and try to picture what we've been given. So we're given the 4th term is 8. Okay, and then the next thing we're given is the 10th term is 512. So the 10th term is all the way out here. So 5, 6, 7, 8, 9, 10. 10th term is 512. Okay. And it says to write a formula for the nth term and use it to find the 15th term in the sequence. Here's the formula. So we still need to know what the first term is. So let's draw that in. The first term is here. Okay. So to get from the 4th term, the 8, to the 10th term, the 512, what do we need to multiply by, right? We've multiplied by something every single time, but altogether, overall, we multiplied by what? 64. Okay, how many times did we multiply by a number? Let's see. 1, 2, 3, 4, 5, 6. We multiplied some number 6 times, and as a result, we were multiplying by 64. Now, this might take a little bit of work to figure out when you're first starting out with these, but you'll also know that 64 is a power of 2. So, if we multiply by 2, 6 times is the same as multiplying by 64. Okay, so that must mean we can work backwards to get to the first term the same way. So if we divide by 2, 3 times, 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1. So the first term must be 1. Okay. So plug this all in. So we have the first term is 1. We know r is 2. So that's the first part. Write a formula for the nth term. Second is to use that formula to find the 15th term in the sequence. So to find the 15th term, we're going to plug in 15 for n. So 2 to the 14th power, which is equal to 16,384. And that is the 15th term in this sequence. All right, next we're going to talk about sums of geometric sequence. Just like we talked about sums of arithmetic sequences, now we're going to talk about sums of geometric sequences. So if you have a finite geometric sequence, okay, so finite meaning there's a clear end to the sequence, it goes up to the nth term, then you can use this formula to find the sum. So remember, the capital S sub n means the sum of the first n terms. Okay, so the sum of the first n terms is equal to a sub 1, so the first term, and then parentheses we have 1 minus r to the n, and in the denominator we have 1 minus r. One thing to note, r cannot equal 1 in order to use this formula. You can also think about what happens when r is equal to 1. When r is equal to 1, well, you multiply each term by 1 to get the next term. It's actually pretty easy to find the sum of that sequence. There's no need for this formula here. So again, the point of this formula is to shorten the amount of time it takes to find the sum of a geometric sequence. If you're asked to find the first 20 terms, the sum of those first 20 terms, then that would mean instead of having to find the first term, second term, third, all the way up to the 20th term before adding them all up, using this formula, all we need to know is the first term, what r is, and which number we're adding up to. So let's take a look at an example. Here we have find the sum of the first 12 terms of the sequence given by 4 times 0.3 to the nth power. Okay, now you could go about doing this and saying, okay, well, this is 4 times 0.3 to the first, 4 times 0.3 to the second, and so on until you get up to the 12th term. Now that's going to take a lot of time. That's going to be tedious. What we can do, though, is we can say, well, I can easily find the first term. That's 1.2. What's r? What am I multiplying by to get to the next term? I'm multiplying by 0.3. So r is equal to 0.3. And we're summing up the first 12 terms. So n is equal to 12. All right, so we have all the information we need to use the formula. So that's going to be 1.2 times 1 minus 0.3 to the 12th. And it's only the 0.3 that's raised to the 12th. Okay, and in the denominator we have 1 minus 0.3, and that comes out to be about 1.714. Okay, so that's great and all. We can find the sum of any finite geometric sequence. What about for infinite geometric sequences? Now, we did talk a little bit about this in our first lesson when we talked about how it's not always going to give you infinity if you're finding the sum of an infinite number of terms, right? We saw that with the 0.3 repeating, right? So how do we actually come up with the sum of an infinite geometric sequence? So here's the formula for it. Now you'll notice one thing that has to be true for this to work is that your value of r, the common ratio that you multiply by, has to be less than 1. Now if you think about it, if r was bigger than 1, what ends up happening? All your terms get bigger and bigger and bigger, right? Which must mean the sum of an infinite sequence where r is bigger than 1 gives you a sum that's infinite. On the other hand, if r is smaller than 1, that means each next term is going to be smaller and smaller and smaller. What that means is that as those numbers get smaller and smaller, you'll actually be able to get the sum of that sequence because those numbers in the sequence will get closer and closer to 0. Okay, so just to note, this formula only works when the common ratio r is smaller than 1. Otherwise, the infinite geometric sequence will not have a finite sum. It will, in fact, have a sum that goes to infinity. Okay, let's look at our next example. So we have an infinite sum here. Right, it goes to infinity, that's the upper limit. It says 4 times 0.6 to the n minus 1. Okay, so again, this could be, you could try calculating this by trying to find a pattern and doing 4 times 0.6 to the 1 minus 1, 4 times 0.6 to the 2 minus 1, and so on and so on. But if we can use that formula, that will be much easier than having to try to find some sort of pattern and try to work from there. So what we need for the formula is the first term, so 4 times 0.6 to the 1 minus 1, which is equal to 4. And we need r, so the number that you're multiplying by, the common ratio, that you're multiplying by to get to the next term. So that in this case is 0.6. So now we just need to plug that into the formula. So we have 4 divided by 1 minus 0.6, and that comes out to be equal to exactly 10. All right, we have one more example. A city of 350,000 people is growing at a rate of 1.3% per year. Estimate the population of the city 30 years from now. Okay, so we know here in this case that in the first year, we're starting with 350,000. If we're trying to find the population 30 years from now, we're trying to find A30. Okay, we know that it's growing at a rate of 1.3%. So that must mean, what do we need to multiply by to get the following year? So we don't multiply by 0.013, that's by what amount it will grow, but it doesn't give the population of the city 1 year later. So we need to multiply by 1 plus 0.013, right? That way we're taking into account the 350,000 that we already have, and then it grows by 0.013, so we add that on. So we're multiplying by 1.013, and now we can plug that into the formula. So A sub 30 is equal to 350,000 times 1.013 to the 30 minus 1. Do the exponent first before you multiply by 350,000, and this should come out to be about 509,028. All right, so you can see how with geometric sequences and sums, we have some similar formulas and some similarities with arithmetic sequences and sums as well. But with geometric sequences, you are multiplying by a number to get to the next number, whereas with arithmetic sequences, you add by a common difference to get to the next number. With the sums, arithmetic sums, there was a formula to find arithmetic sums. With geometric sums, we have to differentiate between finite and infinite sums, and then with infinite sums, it only works when the absolute value of r is less than 1.